Thanks everyone for staying. I know there are a lot of good talks going on right now. So my name is Antonin, as Brian said, and I work for Barefoot Networks, where we make P4 programmable ASICs. So today I'm going to be talking about switch maintenance, switch upgrade, and availability, like Brian said. I'm not going to be talking about hitless upgrade. I'm going to be talking about a different feature we have on Tofino, which is called fast refresh. Because even though we do support hitless upgrade, this feature, fast refresh, covers more general use cases and can be used even when hitless upgrade cannot be used. If you have actually an issue with your data path because of some bad state, you're not going to be able to fix that using hitless upgrade. Or in our case, if you want to actually upgrade your P4 programs, you're not going to be dynamically, you're not going to be able to use hitless upgrade. So I'm going to be talking about this fast refresh feature, how it's supported in Stratum, and how it can be leveraged by control plane applications like the ONF controller. And I'm personally very happy to be talking about fast refresh because as an engineer who actually works with Tofino, this is one of my favorite things to use. So here are the things we're going to cover. First, a quick introduction to Tofino and programmability. Then the Tofino integration with Stratum and why we think there is a good synergy between Tofino and Stratum. Then I'll finally talk about fast refresh, what it is, how you can use it, and why you should be using it. And I think finally the highlight of the talk is going to be, I'm going to be showing a demo video and hopefully I'll be able to talk through it. And what this video is going to show you is how fast refresh can be used to dynamically change the P4 program you're running on the Tofino switch. And I'm going to show how by changing your P4 program, you can achieve better latency or better power consumption. So I'm going to show this live and show some actual numbers. So just as a quick recap, many of you probably have seen that slide somewhere. This shows the PISA architecture. So PISA is not Tofino specific in itself. It describes a new hardware paradigm for switching ASICs. And Tofino is one instance of the PISA architecture. So you start with a programmable parser, which is going to be able to extract arbitrary header from your packet, so either your standard protocols or any protocols that you have defined. Then it goes through a programmable match action pipeline. So PISA defines a multi-stage pipeline, and in each stage you can perform a certain number of matches and actions based on the result of those matches. And those matches can happen in parallel within one stage. And finally, you go through a deparser where you put back together your packet from the initial packet contents plus all the modifications you may have done in your programmable match action pipeline. So now Tofino. What is Tofino? It's the first end-user programmable high-speed Ethernet switch ASIC, which can be programmed by any end user. So the end user can be actually an OEM here, like Cisco or Arista, or it can be, well, an actual telecom operator wants to write their own P4 programs. It's modeled after the PISA architecture, which I've just described, and it's fully P4 programmable. So it ships with a P4 compiler. If you get Tofino, you get access to that compiler, and as long as a program can compile, you know it's going to be running at line rate with deterministic latency. Our flagship product is a 65-100 gig port switch. I have a few of them from different vendors in the demo room. But we also have several SKUs all the way down to 1.8 terabits. And there is no compromise on power consumption. It fits within the same power envelope as a fixed function ASIC, and no compromise on speeds. This is comparable to similar offerings, and obviously that was a requirement to introduce a programmable ASIC to market. Finally, we do have integration with several existing networking operating systems. One of them is Stratum, which we're going to be talking about, of course, and another example is Sonic, for example. So why data plane programming? Well, first is I mean, the most obvious benefit is that you can realize your own ideas, like immediately. It's just like a program away. You just have to write your P4 program like you would write a x86 C program. Then, and that's something we really like to emphasize at Barefoot and also in the P4 community, is that it enables you to reduce complexity. You can get rid of any features that you don't need, or more precisely, you only introduce the features you actually need. And what that enables you to do is to achieve efficient use of hardware resources. Because if you're freeing up resources for features that you actually don't need, some like, I don't know, exotic tunneling feature, then you're free to use those resources for example, to grow the sizes of the match action tables you care about, L2 table, L3 tables. Or maybe you don't use those resources at all, and like we're going to see later, you're going to be able to achieve like sub 400 nanoseconds latency. Also greater visibility. So one of the killer applications for P4 programmability has been like telemetry, in-band network telemetry, which has been demoed in several places. Modularity, that's something which has really been the emphasis of the latest version of the P4 language, P4 16. We try to enable you to write like P4 modules that can be shared and reused across different P4 programs. One like trivial example is how you can define a standard parser for your standard protocols and share it across programs. Portability, because different classes of devices are programmable with P4, SmartNICs, ASICs. I don't want to say full programmability because you can't always run the same P4 program on an ASIC and an FPGA, for example, specifically. But usually you have portability within one class of devices. And for some things, you have portability across classes of devices as well. And finally, another big point is that you own your own ideas and you don't have to share IP. If you come up with a new feature, a new packet processing logic, you can implement it and keep it to yourself in a way. So in this talk, we're going to be focusing on, and in particular in the demos that I'm going to be showing later, we're going to be focusing on those first three bullet points and how they can be exercised on Tofino. So this diagram is kind of like the one Brian was showing. It shows like the current Tofino support in Stratum. I guess I just put like a vendor name in some of those boxes here. So you'll see those three next-gen SDN interfaces, P4 runtime, GNMI, GNOI, talking to the Stratum process. And I won't spend too much time on this, but basically those light blue boxes, BF switch, BF node, BF chassis manager, those have one-on-one mappings to the slide that Brian was showing. And those are the pieces that we have already contributed to the Stratum repo, which I guess is going to be more accessible now and will be publicly available sometime next year. We provide essentially the BF node class, which talks directly to the SDK and controls a single instance of an ASIC, and the BF chassis manager, which interfaces between the platform libraries and the Barefoot SDK. So I think to get things a bit more concrete, here are the things that we do support today. So most of the P4 runtime features, that includes like packet IO, sending and receiving packets from the CPU. Match action programming, of course, but we have like very general support. If you're a bit familiar with P4 and the PSA architecture, we have direct and indirect tables, which are used for different things, and we support both in Stratum right now. All standard externs. By standard, I mean the PSA extern, so that these are counters, 2-rate 3-color meters, things like learnings that you can use to learn L2 MAC addresses and populate your DMAC tables. The only thing which is missing right now in our support, I think the only big thing is stateful registers, which enable you to save and restore state across packets. So if you want to do something on a per flow basis and not on a per packet basis, for those kind of more interesting, not stateless applications, you're going to be using those stateful registers. Just in time for this event, we actually added support for port operational status and port stats through GNMI set and subscribed. So in earlier demos, we were relying on Barefoot proprietary APIs, to query like port state information, port status information. and we've been able to transition to GNMI. And the things for which we're going to add support in the immediate future, it's port configuration through GNMI. So how do you add ports, enable ports? And of course, P4 runtime stateful register support, which I just talked about. So this is a bit of a marketing slide, which talks about why I think you should be using, you should consider using Tofino if you want to deploy Stratum in your network or in your lab. I think I can safely say that we have the most feature complete and compliant P4 runtime implementation at this stage, based on all the things I just described on the previous slide. We've been working on the P4 runtime implementation for a while now, actually for as long as P4 runtime has existed, so more than a year and a half. And our first demo of P4 runtime with ONF was back at SDN NFV World Congress in October last year. We also have support for things that I would qualify as advanced features, such as, which in some cases are optional in P4 runtime and in Stratum, such as dynamic reconfiguration, like pushing a new P4 pipeline to the device in real time without restarting any user process on the switch. And another cool feature is rollback on error for batch semantics. So P4 runtime, for efficiency reasons, lets you push several table operations as one P4 runtime message, as one gRPC message. Those are going to be processed potentially in parallel by the ASIC drivers. And the idea of rollback on error is that if you get an error on operation number 78 in your batch of 100 operations, well, all the operations that have already been committed to hardware are going to be rollbacked. And so your switch, what that tells you is that when you get the response from the server, which can be OK or error, you know exactly which state the data path is in. Either it's the stage before the batch update, if there was an error, or if it's the state after the batch update was completed, if everything went through. So I've actually been authorized to give a performance number here. The last time I benchmarked our P4 runtime implementation, which is not fully production ready yet, we were able to get up to 100,000 new flow rules per second added to hardware to completion when we're using P4 runtime batching. So with some caveats based on exactly which memories you're writing to. Obviously, if you're writing to TCAMs and there is a lot of shuffling happening, that performance is going to take some impact. But if you know the optimal order to populate your TCAMs, or if you're actually populating exact match tables, you can get close to that number. Also, Barefoot has been an active contributor to Stratum for a while, and we're committed at this stage to keep releasing code and open sourcing top-level SDK interfaces. So we've not been shy about pushing code into Stratum, which is directly calling into the Barefoot SDK. And I think my timing is pretty good today because we just announced our second generation chip, Tofino 2, which is a 7 nanometer, 12.8 terabit ASIC. And so we are committed to carrying over the support that we have in Stratum for Tofino 1 to Tofino 2. And I think that proves that we're able to deliver multiple generations of silicon, and we'll keep supporting them in Stratum. So now let's cover what Tofino Fast Refresh is. So if I were to summarize it in one word, it's basically a way to reset your state on your switch, whether it's hardware state or a state which is in software in your drivers. And basically, it lets you start from a complete clean slate. Now, a major objection would be, yes, but doesn't that mean that my traffic is going to take a hit? And what I'm going to show with my demo video is that the traffic interruption is actually minimum. So when I say you reset your switch state, you can either start from, because you start from a clean slate, you can either start from the same P4 program, which can be useful if you have some unexplained issue in your data path and you want to reset things, or you can start from a completely new P4 program, which is a feature which is specific to Tofino. It's a simple three-step sequence. First, you just give the P4 compiler outputs to Stratum, which hands them over to the drivers. This is done through P4 runtime. So once again, either these are your same old compiler outputs or the compiler outputs for a totally new P4 program. And the second step is the forwarding state is going to be completely rebuilt using your regular P4 runtime API calls. So it's important to see that even though this step can take a while, I mean, it's easy to see because you can have millions of flow rolls in Tofino, right? And I just gave on the previous slide a performance number, which was 100,000 flows per second. So if I have like 5 million flow rolls, it can take up to like 50 seconds, I think. But during that step, traffic is not interrupted. So all your packets are still processed by your previous data plane and your previous forwarding rules. And the first step is, well, now I'm ready. I want to move over from my previous data plane to my new data plane. And so in this step, we actually perform the core reset on the ASIC, on the chip, and we rewrite all of the memories through batch DMA. And it's during that step and that step only that you're actually going to see traffic loss. Now, because we use batch DMA, this step is actually pretty fast, and we're able to complete that whole operation with less than 50 milliseconds of packet loss, which is pretty good. And those milliseconds, it applies for any P4 programs that you're switching to and any set of flow rules. So there is no like trick here. Whether you're starting from 10 IP4 entries or you're actually writing millions of entries, it's still going to be 50 milliseconds. So fast refresh is actually facilitated by a new generation of program-independent APIs, and one of them is P4 runtime. We also have like some proprietary extensions to P4 runtime, I would say, that are called BRI, Barefoot Runtime Interface. And so why is it useful to have program-independent APIs here? It's because, well, if you're switching from one P4 program to a completely different P4 program, which is one use case for fast refresh, if you're auto-generating APIs, which we used to do early on at Barefoot before P4 runtime, then you actually need possibly a lot of changes in your control plane stack, right? Potentially what we used to have is you would need to unload a DLL, which would be the generated APIs for your previous P4 program, regenerate the new one, and then reload it into your process. And obviously that's going to have an impact on everything south of the drivers, right? Like right now, for example, in ONOS, they have the ability to use the same L3 apps for different P4 programs by doing a simple mapping between some logical tables and some P4 tables. Well, if you're actually using generated APIs that depend on your P4 program, the smallest change in your P4 program can impact your APIs, and that kind of reusability goes away, even for simple things like L3 forwarding. So it can be leveraged by all network operating systems. I mean, Stratum has been my favorite playground for this, but it can also be leveraged in Sonic. In Sonic, we can support multiple profiles with different table sizes, and we can use that fast refresh feature, well, either to do a reset in case of issue or to move from one profile to another profile without recompiling any code, save for the P4 code, and without disturbing the Sonic process and the Sonic applications. So why use Tofino Fast Refresh? Well, it's a unified and resilient mechanism to upgrade software. And I think one of the novelties here is when I say upgrade software, that upgrade can include my P4 program. It may or may not include my P4 program. And you can upgrade everything, whether it's your driver stack, control plane stack, or even your Linux OS through kexec, which is going to force your user processes to shut down. You can load a new kernel version, restart your Stratum process, and all you're going to see is those 50 milliseconds of packet loss. And we claim it's bug-free upgrade. I think it's because unlike something like itless upgrade, which we do support also, this whole process is pretty straightforward. There is not going to be any leftover state, or, well, itless upgrade may cause issues in some simple cases. For example, on Tofino, even if you have the same P4 program, if you move from one version of our compiler to another version of the compiler, it may change how resources are allocated on the ASICs. And in this case, doing something like itless HA H-less upgrade, sorry, becomes like kind of problematic because you have to be able to read the current state in the hardware using like your old resource allocation and then transform it to a format that works for your new resource allocation, and things can get like complex. And once again, I think I wrote this. This is great for schedule maintenance. If you just have, so first, if you just have some mysterious data plane issues that you want to solve, it's a perfect fit for you because you're going to start from a clean slate. It's also great for schedule maintenance because that I would claim that that 50 millisecond window in the worst case is good enough to stay within SLA budget and not be afraid of rolling out some complicated upgrades that can be achieved through fast refresh. So now, if you're using like an OEM product, which is built using the Tofino ASIC, when you get software upgrades from the OEMs, these upgrades can actually include data pass upgrades, which is pretty novel and interesting. I mean, one popular use case, as I've been talking about, is to actually change the role of the switch. But I mean, let's be real. How often are you going to be changing completely the role of a switch in a data center network? I mean, if the switch is a Tor, you want it to behave as a Tor. But you can have some minor variations, like in terms of table sizes, disabling some features, like improving your packet processing. All of this is possible through P4 and fast refresh. And as I've been talking, so yeah, I think it's a good summary that fast refresh enables you to support multiple data plane profiles in a network operating system and also different upgrade scenarios based on what you're upgrading. I think this is kind of like a picture of what fast refresh actually looks like in P4 runtime. So you start with your P4 runtime controller. At first, your ASIC is running your first data plane with your first set of forwarding rules. You're going to do a P4 runtime safe forwarding pipeline RPC call, which is going to push the output of the P4C compiler for your new data plane, which I show in the top right corner as data plane 2.p4. At this point, your drivers are going to start accepting new flow rules, for your new P4 program. But at the same time, your ASIC is going to keep processing packet with your old P4 program and your old set of forwarding rules. So as I said before, no traffic interruption. When you're ready, you're going to do, and this is the third step and last step, a new P4 runtime RPC called set forwarding pipeline with a commit flag. And this flag just says, OK, I'm ready to switch over to my new pipeline and my new forwarding state. And that is when you have like 50 milliseconds of packet loss. So I'm going to show a video of a demo. I'm going to have to accelerate a little bit. But in this video, I'm going to switch between 4 different P4 programs. One of them, the first one, is fabric.p4 from the ONF with SP gateway offload enabled. So SP gateway offload is the offload of user plane VNF functionality to the data plane. All the features are described on the right. I have about 260,000 flow rules stall for this program. The second program is actually the same program, fabric.p4, this time without SP gateway functionality. So we have actually like less feature and fewer flow rules. The third program is a very easy, simple L3.p4 program, which I wrote myself, which is able to do some IPv4 routing on like 200,000 routes with 65,000 next stops. So it's really using like few of Tofino hardware resources, I want to say. And the next program is just like a more advanced version of that L3 program where I kind of try to, actually I just look up online like what was the current size of the internet routing tables. Maybe you probably know that this size like keep increasing because as we run out of IPv4 addresses, we actually have some disaggregation of addresses like geographically, and that means that prefixes actually become longer, right? And so in this case, I was able actually to fit more than 1 million IPv4 routes in Tofino, and that's used like less than 30% of the resources of a single Tofino pipeline. And this is a setup I'm using for the demo. So at the top, you have our switch under test, which is a 3.2 terabit switch. And at the bottom, you have another Tofino switch, which because of P4 programmability, I'm actually able to use as a package generator. So this switch is literally used as my tester for this demo. What it does is it generates a 100G stream of 64-byte frames. For each packet, it's going to measure latency and sample those live results to some kind of CLI application, which I've written, which is called package and CLI. And it's also going to measure packet drops. And by measuring packet drops, I'm going to be able to say what was the window of packet drops for my fast refresh. So let me jump through the video. I'm not going to be able to pause through it too much because I'm running out of time. Do you think you can start it, Brian? So on the right side, we have our package gen CLI tool, which is going to measure latency and everything. And on the left side, we're going to run a P4 runtime client. So at the beginning, you can see on the right that Rx is 0. We're actually dropping all the packets, and that's because no P4 program is running on the switch. Sorry, I have to talk fast. On the left side, you can see that all those 4 P4 programs that I've talked about, I have pre-compiled them to save time here. And I'm going to use, oh, thank you for stopping. And I'm going to use P4 runtime and fast refresh to swap the P4 program. So right now, no P4 program is running, and we're dropping all the packet. Now, this command is going to do the fast refresh using P4 runtime. The inputs, I'm not going to go into details. These are just the output of the P4 compiler. Yeah, you can resume. Thank you. So we also have some static entries to ensure that we have connectivity and we can go back to the tester. So can we just pause for 1 second, please? Here you see some interesting output. I won't pause for the next programs, but we get an estimate of the power consumption for this specific program by the match action part of Tofino. In this case, I'm not allowed to give absolute numbers, sorry, so I have to give like relative numbers in terms of the max possible power consumption by the match action pipeline in the ASIC. So at this stage, with this program, we're at 53%. And you can see the different steps. I mean, everything goes very fast, even though we have so many entries. Basically, at this stage, we've already completed the fast refresh. We've written all of our forwarding entries to the ASIC. And if we can resume the video and go on the right side, now you can see that our Rx rate is 140 million packets per second. So we're not dropping packets anymore because we have that program. We can print the latency for this program, and here's the median latency is about 680 nanoseconds. Now what we're going to do is we're going to reset the stat counters in our tester CLI tool. Just so that I can actually print the stats after I do my next fast refresh, and we can see how many packets were dropped. Okay, so far, no packets dropped. We see that the diff between the TX and RX counter is 0. And now we're going to be able to do a fast refresh with our second program, which is fabric.p4 without SP gateway. So same thing, we do the fast refresh using P4 runtime here, give some static entries. Now our max power usage is 28%, and we are writing 110,000 entries. Why is it less? Because we disabled the SP gateway offload. We don't keep subscriber connection on the chip anymore. Here, you see the packet drop window is actually less than 31 milliseconds. So I did say 50 milliseconds. That was to be conservative. In practice, we see things more like 30 milliseconds. We're going to show the latency. Because I've removed some features, I would actually expect latency to be a bit less than it was previously. Before it was 680 nanoseconds. Now we see that we're at about 640 nanoseconds. I'm going to reset the stats counter, and now this is going to be interesting. We're going to move to our very simple L3.p4 program, which is just doing L3 forwarding with more than 200,000 routes. So we do fast refresh again. This time using L3.p4. We do have some static entries as well. Now the power consumption is very low because we're using very few of Tofino memories. We're at about 10%, and we still have almost 300,000 entries. We're going to print the stats, and we see that even though the P4 program is completely different, the number is actually here. The number of packet drop is actually in the same ballpark, and it's a window of 31 milliseconds of drops. Now the latency is completely different now because we're using so few features. were at 370 nanoseconds. And let's just, do the last program now, which is L3heavy.p4, which actually has 1.3 million IP4 prefixes of different sizes. As I said, kind of like the same size as the internet routing table. The power usage is going to be a little bit higher. It's 18% right now, and we have 1.3 million flow entries total. And this is the last time we're going to show the amount of packet drop. It's 30.29 milliseconds. Once again, very close to what we've seen all along. It's pretty consistent because we're essentially initializing all of Tofino's memories. We're going to show latency for the last time. Interestingly, even though we have many more entries, the latency is very similar. It's 365 nanoseconds. It's actually a little bit less than before. And this is because of Tofino architecture. Actually, we are doing a lot of lookups in parallel here. So that's actually not penalizing us from a latency perspective. So I'm going to just skip this very quickly. This is just like a recap of everything I've shown in terms of power consumptions. The packet drop is consistently less than 31 milliseconds, and the latency really depends on your P4 program and how you organize your lookups. So the takeaways from this talk is that you can use fast refresh on Tofino to update P4 programs, upgrade any kind of software that includes data plane software as well, and reconcile state with minimum traffic interruptions, about 30 milliseconds, which in my opinion enables you to do some crazy upgrades on a weekly basis maybe, and stay within your SLA budget, even at the TOR, obviously at the spine. You can change your P4 program without modifying any x86 code running on the switch, thanks to our new generation of program-independent APIs like P4 Runtime. Fast refresh can be leveraged by any NOS, Stratum, Sonic, and so on. And I've just shown in the demo that you can write different P4 programs and change the switch role using fast refresh to optimize for different things in different dimensions like latency and power. And I think the cool thing in this demo, the little extra, is that because of P4 programmability, I'm actually able to use a Tofino ASIC as a tester for a different Tofino switch. And I test Tofino with Tofino, measure things like latency using a Tofino ASIC, which has been programmed to act as a tester and a packet generator. Thank you for listening. And I'm really sorry I went over time a little bit here. Maybe we can do one question if there is a question.
Awesome. Thanks, Antonin. That was a really interesting demo, and it shows Stratum working in practice with real hardware. So, yeah, as Antonin said, we have time for just one question. If there's anyone in the audience with a question, in the back.
Better be a nice question, Andy.
It's a nice question. It's a nice question. I think it's nice. So I think you mentioned in a slide you showed. So there's the longer period of time before the 30 milliseconds begins, and the new table entries from the controller are going to the new config. But can it be copied to the old config during that time as well, I assume? Or is that an option in the software to pick whether it goes to both or only the new one?
Sorry, can you say that again?
During that, let's say, 10 to 20 seconds where you're loading up the new one in the software before the fast refresh, can the new table entries also be going to the current switch state as well simultaneously?
That's a very good question. So with the current implementation, as you're moving to a new data plane and you're starting to replay some new forwarding state, basically, even though your data plane is still processing packet using the old program, you kind of lose all ability to talk to hardware during that phase. So you cannot add new forwarding entries. I think that's something we could technically do. And I think one thing which we're missing right now and that would be very useful for people is the ability to get like port status notifications during that upgrade window and be able to react to those because that's something that's important in an actual production deployment. So there's nothing preventing us from doing this in our hardware and in our software. We're just missing that feature at this time.